Welcome to the next lecture. In this lecture, we will continue our discussion with intersymbol interference and pulse shaping. Before that, we will briefly discuss something called line coding. So what line coding means is, if we recall the steps for conversion of analog signal to digital one, so the first step is sampling, and then sampling is followed by quantization. Quantization is followed by pulse code modulation, right? So what it means that instead of an analog signal, now you have series of ones and zeros, right? Now how to represent them in terms of waveforms, because at the end we have to transmit it, we have to process it. That procedure is called line coding. So there are several ways to do it. One way is we can represent 1 by some positive voltage level V and 0 by some minus V, negative voltage level. So this waveform does not return to 0, in the sense we don't represent 0 by 0 voltage level, either positive or negative, so it's called non-return to 0. So there can be another possibility that you represent 1 by positive and then 0 by 0. So this is called return to 0, RZ, and this will be called NRZ. And in fact, return to 0 can have one more way, that a positive level is determined by a bipolar signal. Suppose if this interval represents 1, that means there will be this positive to negative part. Okay, for this remember that the pulse interval is some t. What is bit is represented by a pulse interval t. What is the amplitude of the signal in the pulse t, for time interval t. So 1 represented by this bipolar and 0 is represented by 0. Then again 1 is represented by so 1 is represented by this. So this is called bipolar return to 0. So definitely this will be called unipolar return to 0. Unipolar because one particular bit is represented by a single polarity of signal, positive or negative. In bipolar, it is one is represented by a signal which has two polarities, plus and minus. This also is unipolar. And if we have a sort of bipolar with non-return to 0, that is this plus V minus V. So what is the thing? So plus 1 is represented by a shift from positive to negative, this is 1, and a shift from negative to positive will be represented as 0. Okay, a shift from positive to negative represented as 1, a shift from negative to positive represented as 0. So this is of course bipolar, non-return to 0. It has a special name, it's called Manchester. Okay. So with a motivation or with an inputs from our previous lecture, where we proved that a train of rectangular pulses has the power spectral density which has a flavor of sinc function, all of these signals will have a flavor of, if you plot their power spectral densities, that will have a flavor of sinc functions. But we will not prove it, but we will take a fact that by having these different combinations, like non-return to 0, return to 0, then bipolar and polar, they have some effect on bandwidth of those signals. Okay, suppose if I will plot here sorry, let me first plot the unipolar non-return to zero. Okay, its power spectral density will look like this. So we are taking this fact, we are not proving it right now. So it will be something like sync. Okay. Now, if we plot this is the this is unipolar non-return to zero. Now, if we plot return to zero, see return to zero will have, so this is NRZ. Of course, I will call it unipolar. Now, let me plot unipolar return to zero. So that will have something like this. Okay. And finally, Manchester line codes have power spectral density, something like this. Okay. So we see that Manchester line codes, they don't have too much side lobes. Okay, whereas non-return to zero has side lobes also. So not efficient use of bandwidth is here. So this is one important factor when you convert your pulse code modulation bits into some line codes. So we have to decide which line code we have to use. Although in wireless communication it doesn't affect too much, but when you have to communicate over LAN or other, it affects. Okay. Now, the other important problem which we discussed last time was of inter-symbol interference, right? So today we will discuss about a criterion to overcome that. Let me first again recall what is inter-symbol interference. Okay, it's a very simple concept. Inter-symbol interferences, now you saw the line codes. Okay, so we represent them with rectangular pulses. Now whichever line code you use, you are basically transmitting you can say a series of rectangular pulses, train of rectangular pulses over the channel. Now, as we discussed last time, a channel can be thought of as a sort of a system with some transfer function. Okay, so here is, so a channel, communication channel is equivalent to a system. If you recall your signal systems, any system is represented by channel impulse response, by impulse response, and it has a transfer function, right, h of f, where this h of t and h of f, they form the Fourier transform pair, right? And we can have input to the system, that will be channel input, and we have output to the system, that is channel output. What is the characteristic of usual wireless, ideally the wireless channel? Okay, the main thing is each channel has is fit for particular frequencies. I told this last time also. Suppose if you take telephone channel, that is your wire line, that is represented by transmission line. Okay, a pair of transmission line can be modeled as a parallel capacitor, right, and some resistor. Okay, and of course there will be some inductance also. This is the equivalent representation of a transmission line if you have done it. Now, what is this equivalent in terms of filters? So you have a parallel capacitor and you have a series inductor, right? So for low frequencies, they get easily transmitted over this particular pair of transmission line, but high frequencies will not get. So it is sort of a low pass filter, right? So this channel characteristic can be represented like this. Okay, it will not transmit higher frequencies. So similarly, wireless channel also have similar transfer function. Every channel passes only particular frequencies. And now you see, if you see the optical fiber communication channel, that can be represented as a band pass filter. right? Because optical channels, yeah, they only allow very high frequencies. They will not allow low frequencies. Whatever be the case, ideally a channel characteristic in frequency domain can be represented as a sort of a rectangle. Ideally, that is, suppose if B is the channel bandwidth, so this is the system transfer function of the channel. It will have some, so what here we call as bandwidth is, it is the permissible frequencies which a channel supports. Okay, suppose in case of telephone line, if you see this particular equivalent model for transmission line, suppose you neglect the inductance, okay, for a time moment, you just represent the transmission line by equivalent capacitor, and you know that its cutoff frequency fc will be dependent on 1 over rc. Okay, in fact cutoff frequency will be some constant times rc. You can find that constant. So it means we can effectively say that the bandwidth of channel is fc. Okay, because it will I am showing it ideally here, it goes down, but practically it may go something like this, right? So at fc it is going below 3 dB point, and then it slowly decays. But this is the theoretical actual one, but theoretically we can say that a channel transfer function is represented as a rectangular function, and depending upon the bandwidth of channel, it will only pass signals up to bandwidth p. Okay, and when you are transmitting, now see, this is the frequency domain. What will be its time domain? You know that will be actually a sync function, right? Now if you look at any NRZ, suppose, okay, or return to zero, whatever you look at, they have a sync flavor. We call it sync flavor in time domain, sorry, in frequency domain, right? So they are rectangular functions but sync domain. Now if you see, since they have rectangular waveforms, they are rectangular waveforms, and this is the transfer function of the channel, so its equivalent effective you can say channel impulse response will be sync, right? Now what happens that you have h of t and you have these waveforms, suppose x of t. What will be the output? Y of t. So y of t will be the convolution of, so you are taking convolution of rectangular pulses with sync. Okay, see, I recall why is the sync there? Because channel impulse response of communication channel is usually represented by a rectangular, suppose a low pass filter. Okay, so its impulse response is sync, and when you pass anything through the channel, the output will be the convolution of input and channel response, impulse response, h of t. So what will happen is, at the receiver you will not get rectangular pulses, rather you will get these syncs. So if there were, suppose this was 1 and this was 0, okay, then this was again 1. So at receiver you will get something like this. So there is possible overlap, right? Suppose this was, if you alone represent just 1, okay, so this can be the time interval t. Now at this time interval, right, so here is the overlap. Then again, so receiver may not be able to decode it properly. Okay, so there is a intersymbol interference between the symbols. Now how to undo this? This is what Nyquist asked this question. So to answer this question, what I can see that a genius, the step is, see what he said is, you are basically sampling, right? You are not transmitting continuous time signals. So what Nyquist suggests is that if you represent the complete system, so transmitter, channel, and receiver, okay, you treat this as now a complete system, and you call its overall impulse response as H effective of t. Okay, now what Nyquist suggests is that the effect of intersymbol interference could be completely nullified if the overall response of this whole communication system, that is, which I have written there, transmitter, receiver, and channel, which is represented by H effective. If the overall response is designed, that is H effective of t is designed so that, at every sampling instant, at receiver, of course, the response due to all symbols except the current symbol is equal to 0. Now, how can I represent this mathematically? Suppose I will bring in some notation. Suppose TS is the symbol period, right? So I actually sample after every TS time intervals. Okay, that is sufficient for me. And then the effective impulse response, right? Since I'm sampling, so I will use discrete and TS. Now this should be equal to what, right? So at n is equal to 0, so n is equal to 0, actually it corresponds to the current symbol. Okay, so that should be equal to some constant k for that, and for all other n it should be 0. This is what it means mathematically, that the response of all other symbols, right? Because see, even the sync function can be calibrated in that way if you properly choose parameters. So suppose this is the time interval. So suppose I am having, okay, so this is one time interval. Now sorry, so I can, so this is TS. Okay, so this is TS, and then this will be, suppose 2 TS, this will be 3 TS. Okay, so what we can do is the other symbol can be chosen such that if you see the response of that will be something like this: 0 at this point, again 0 at this point, Okay, so the contribution of other pulse at TS to TS is 0. That is important. Okay, now if you see here, suppose it is here 3TS, so this is the turn of this pulse. Okay, so the contribution of first pulse here is 0, but the second pulse is there. Okay, it will become more clear as we do some examples. So now to get it even more clearly, what we have some representation. Suppose P of t represents the pulse shape of symbol. Okay, so in our case, if you have a simple rectangular pulse, so P of t is simply a rectangular function. Okay, and hc of t, let this be the channel impulse response of channel. So impulse response of channel, and hr of t be the impulse response of receiver. Okay, then how can we represent the effective transfer function of system? See, one is that this pulse gets transmitted via the channel, and then it is passed on to the receiver, right? And you want a condition, you have to look at this condition that H effective and TS should be equal to K only at n equal to 0. For this to happen, the effective channel response is as if you are also XORing delta of t with the pulse. See, it means that H effective of t will be delta of t convolution with pulse function, then definitely convolution with hc of t, and then convolution with hr of t. Now see, convolution of p of t, hc of t, hr of t is clear because it's a usual signal system concept. When you transmit input x of t via a system with impulse response h of t, then the output is convolution of input and channel response. But what is this delta of t? This delta of t actually guarantees, this is what guarantees that the impulse response is non-zero only at t equal to 0. That is when the current symbol is transmitted, and it is 0 for all other t. Or if you sample it, it is 0 only at n is equal to 0, and it's non-zero at n is equal to 0, and it is 0 for all other symbols. Okay, and from this you can actually find its Fourier transform, right? Then you will get the transfer function, overall transfer function, effective transfer function of the whole communication system here end to end. Okay, now as an example that will make it a little bit clear, suppose if you chose your effective impulse function as sinc of, maybe you can write it as pi t by ts, that means sine of pi t by ts divided by pi t by ts. Okay, so now if you sample it, so what will be H effective of nts? That will be sine of pi n, so ts and ts will cancel, divided by pi n. Now this satisfies, you see, H effective of nts. Now this sine pi n by pi n will be equal to, So if you put n equal to 0, you know that then you have to compute the limit sine of x by x, which is 1, so it is 1. And if you put, if n is not equal to 0, rather n is equal to 1, 2, 3, for all other n, sine of n pi is 0. For n is equal to 1, 2, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, so it is 0. So this is one particular choice. So here you have to choose this ts, and you have to write the sinc function properly. So if you suppose instead of ts, if you don't write ts, if you write some other time, suppose you write some maybe root of 3ts, okay, suppose, then this will not work, right? If you have sine of pi t by root 3ts divided by pi t by root 3ts, so then definitely you will see that this, for this particular channel response, the channel response of other intersymbols which are being transmitted at the same time, they will interfere, and this will not be 0 for n not equal to 0. Okay, so you have to properly choose the channel response. Sorry, there was some error, so that is why I couldn't get record for a few moments. Okay, now there are some important conditions which this transfer function. One condition is that this the effective channel response, it should decay at a faster rate, near the samples n not equal to 0. What it means is, of course, so this is, suppose n is equal to 1, you are ensuring that if we have some other signal here, you are ensuring that this is the value of because the impulse response of other signal is 0, but the decay, that means this thing, these at this point, if you have this, yeah, so the decay rate of these pulses, it should be fast. It should not be slow. That is one important thing. And the other important thing is that, suppose to get into that, we first derive, or we first get the effective transfer function, sorry, h effective of f. So what it will be for the case when h effective of t is sinc of pi t by ts. Okay, you know that it will be a rectangular function f by fs times 1 by fs. Okay, so you can easily check. Actually, you can write this as sinc, then you have this 1 over ts times t, right? It also can be written as sinc fst, where fs is equal to 1 by ts. Then you know the formula. Its Fourier transform is 1 over fs rectangular function of f by fs. So it corresponds to, again, of course. Now what is the difference? This also is a rectangular function, but we have here this point as fs by 2, this as minus fs by 2. Okay, so we have chosen properly this frequency fs. It corresponds to 1 over the simple time period. Again, if you choose this fs to be some other value, okay, then it may not result in the intersymbol interference cancellation. One important thing is that, first of all, the difficulty with this, if you look at it from filter point of view now, then H effective of T is a non-causal system. Communication systems, we want usually the causal ones. Okay, so it means that even for t less than 0, this function exists. Okay, although we start everything at t is equal to 0. The other issue with this particular type of, you can say, the transfer function is that we ensure that at the zero crossings are at the multiples of NTS, right? So if there is sampling error, suppose, then slight sampling error will result in again ISI, because it means that you are not sampling you are trying to sample at TS, but there is some error, so I can write T delta, right? Then sync of this N TS by T delta, this may not be 0. Okay. Definitely. So these are the two issues. So what we would like to do now is, now we would like to see that how can we avoid this. That is, how can we get a transfer function, or how can we shape up the pulse such that these two effects we are able to nullify as much as possible. That I will show in the next subsequent video.